Okay, let me start with my presentation. In this presentation, I will be mentioning about what Cohen did in his work with history of noise in signal processing magazines in IEEE. I would like to start my presentation with his, I would say, the summary of the whole paper. It will be a dull gray vote without noise. I think that one of other friends in this group, she also like found this very much a good one, and she shared it with us. So I will go in the order of how Cohen put things in his paper. To start with, I would honestly say that he put a high amount of stress that he thinks that in order to truly learn about an idea, it is the best idea to go and find the originator of that idea, the originator or the producer of that such idea or theory, and then go back and find that paper and read it, because he thinks that they are very much able to get a sense to get to the essence of the subject with very much simplicity and clarity. And he gave some examples for them. As you can see, their pictures: Einstein, Langevin, Ornstein. Ornstein he's not a signal processing guy, I would say. He's a scientist interested in brain studies, and there are many more he gave examples of. So he continued with the three miracles in 1905. One of them being the Brownian motion, which within which he proves the existence of atoms. And then another one is another breakthrough in physics, explanation of photoelectric effect with introduction of photon, while the definition of photon was made later in other years. So the second paper, it's an instrumental idea that developed the view of matter and light, and which led to the development of the quantum mechanics to nowadays. The third one, as we all are aware of, is the special theory of relativity, which changed our view of space and time with the very much famous equation E_mc squared. He had 5 papers, but 4 of them were pointing to these 3 miracles, I would say. Not I would say, but Cohen, as Cohen said. So he continued with our course is random signals and noise. So then I tried to grab what is related with noise. So Einstein had a contribution in noise area in his two other papers of his at 1914. So in one of them made the formulation of Wiener-Khinchin theorem, by which he relates the autocorrelation function with the powered spectrum. I put some images from Wikipedia or some online sources to give the idea. So he also had another quote regarding this, saying that Einstein was perhaps the first who defined the autocorrelation function. Cohen says that there are some other guys who tried to make the definition, but Einstein was the one who professionally or scientifically tried to put it. Then he moved to discussion of the Brownian motion. So the Brownian motion was first observed by Gui, I would pronounce, I don't know how to pronounce correctly, but he was the first observer of the phenomenon, which wasn't scientifically, but Robert Brown was a Scottish botanist who observed them by by observing the pollens on the droplets of water. I've also put this Brownian motion, a real simulation of it, which I found very much fascinating to watch. Okay, but he also points that Einstein was the first theoretical explainer of Brownian motion based on the kinetic theory of gases with his work in 1905, which is one of the miracle year studies. So he continued, he took the time back to the journey of what is atom, what is the matter made up of. So he moved on to Lavoisier, Dalton, Gay-Lussac, and Avogadro. Avogadro was very much on his work for defining the number of n, but he didn't become famous with what he did, but he became a famous guy after he was dead, sadly, let's say. So according to Avogadro's key idea, a fixed volume of gas, if you put like any kind of gas in a fixed amount of volume, it would contain the same amount of number of atoms or particles. So which is now known as Avogadro's number. So he continued with Clausius for on heat and thermodynamics. So Clausius was the first guy who came up with the first stochastic quantity, which is the mean free path regarding the noise. So similar to noise in a system. Another quote from Cohen, when molecules collide, this can lead to hindering of their forward movement. So as you can see over here, these red dots, let's say, while they're on their way, they just hinder with some other, they are hindered by some other particles, so that I will kind of connect this with the coming theories. So Maxwell came up with an idea saying that, okay, these particles move, but their moving gets closer, converges to Gaussian distribution. But in other words, is the Maxwellian distribution. Then Boltzmann came up and said, okay, but why is it Gaussian? Should it be Gaussian? So Max Boltzmann derived the equation for how molecules' movements evolve into a Maxwellian distribution. So he answered the question of himself by the concept of randomness. Gases reach a state of balance, and then while deriving this equation, he also found the influence of random collisions over molecule speed and positions. So that a new branch of mathematics was developed, which is the stochastic process. So here's the final equation of his, which this is another quote of Cohen, which I found very much. It's very much addressing and very much neat, very much clear. For those who do not know this equation, which I didn't know as well, it must be stressed that it is one of the most important equations in physics, astronomy, chemistry, and plasma physics, and we could go on and on. We could go on and on. So Boltzmann continued his work with in thermodynamics, with introducing the entropy, which measures the irreversibility of the matter of a medium. Clausius has introduced it in 1865, to correct myself. So then Boltzmann made the contribution by looking with the perspective of theory, atomic perspective. Then he came up with the equation, which S is equal to K log W. People also had put it on his tombstone. So this definition states that it reveals how entropy is related to how atoms behave statistically. So Cohen continued with Einstein's contribution to Brownian motion. So we said that Einstein was the scientific guy who made the most scientific and most professional way. He put it in the most technical way. So by giving this definition, he gave the probability of particles being at a certain position and time. And by solving it for impulse response, we have this. So we also have the definition of impulse, delta function of position at time 0 normalized to n. So another point which we have to stress is that Einstein made, as I put here, noise can be used to measure a deterministic number n, which was previously described by or defined by Avogadro, which is one of the most important number in chemistry, in general science. So you can see the derivation of Einstein until he finds the n in terms of some variables which are known to be deterministic, as at the last stage over here. So as a conclusion of Einstein work, statistical properties of heavy particles are the same as the statistical properties of the smaller particles that are too small to see. So by observing the larger particles, the statistical behavior of the larger particles, heavier particles, we can also have an idea about the behavior or statistic about the smaller particles. This is also like the way Einstein himself derived, like, proved that the atoms do exist. Then we can move to Langevin's work. So he came up with a new method for solving the stochastic differential equations. As I wrote here, he tried to put things using Newton's method. As this is another way of writing ma equals to f. Here x denotes the random irregular force. So it's the first time of Newton's equation being introduced or being defined, described with a random force, random variable, let's say. So the key difference between both Langevin and Einstein method is that Einstein method is easier to use for higher order moments, while Langevin's method is easier for smaller amount of moments like mean and variance. As Cohen put another example for equipartition of energy, for a box with elephants, mosquitoes, and molecules, in equilibrium conditions, all of them will have similar statistical behavior. This is why Brownian particles, which are large particles that behave like molecules, can be used to prove the existence of molecules. I can continue with the developments which are closer to the common year. I mean, to nowadays. So Cohen continued with noise, how noise does exist in stock market, financial engineering, economics, electrical engineering. Bachelier, Scotty, Johnson, and Nyquist with giving his previous works. Bachelier was the guy who was very much famous for origination of stochastic processes and mathematical finance. He was very much interested in stock prices. So Scotty and Johnson, the effect of noise in electronic devices for shot noise and thermal noise, and Nyquist criteria for stability. So Fokker-Planck derived a definition or a theory for, it's a differential equation for the probability distribution, how the probability distribution evolves in the domain of time. This is another simulation of it. I could say I also included the impulse response of the solution. So also he had a notice for Fourier's contribution to the area. Okay, we do wonder about signals, but signals has also another property for frequencies, and also Fourier was the guy who introduced the idea for representing a signal in terms of its summation of sines and cosines. Then his Fourier series expansion diverged to Fourier transform. Sorry for my mistake. I can continue. Then we have the Wiener process. At this point, Cohen said that there is a how to say contradiction between the physical Brownian motion and mathematical Brownian motion, and here the Wiener comes. Wiener defined the process, but the difference for Wiener from Brownian motion is that Wiener formulated a measure description for the paths, so that we have the Brownian motion, but for each particle, we can have a formulation for a measure for the description for the path, what path they will follow. So there is a mean zero process for t minus, like for now, and for a delta t after now. There is a mean zero process that the particle will follow. So I have the last 3 slides, I could say. So Cohen continued with the later developments with matched filter, which is widely used in communication systems, such as radar and sonar. And astronomy, as Cohen put it, noise is extremely important in astronomy, as the signal we would like to extract from the total signal is very weak in total compared to the signal, so that noise studies which were done in this area have also made a very significant contribution to the general area, because the scientific people in astronomic area, they had to develop it a lot so that they could use it. So last but not the least, he also mentioned the noise in quantum. He says that in summary, he says that the noise in quantum world is totally different from the noise we know in general. So the developments in quantum world have also contributed to our understanding in the real world. So as a conclusion, I myself found his paper, Khan's paper, a very comprehensive one for explaining the main players from the very back in history till now. He emphasizes the significance and potentials for future innovations and inventions. So that's all from me. Thank you for listening. It's 15 minutes. Okay.
Mehmet Ali, good. This slide presentation was pretty balanced.